Hello everybody, I'm Elior, and today we're going to talk about shifting the focus from data quantity to data quality using something called data maps. So a bit about myself, I'm the CTO of DSG, as Tal presented me, and what we do in DSG is we help organizations succeed in their AI endeavors in their data science processes. And part of that is always keeping up with the latest advancements in the relevant fields and obviously with academic papers. So what we are going to be talking about today is our journey, taking a specific paper, applying it to the real world, what we've learned from it, of it specifically, and some more experiments and more research we made on top of that paper. And I hope you can take something from that to your own work. So before we start with the paper itself, I want to talk about a specific problem. So let's talk about data quantities and how they behave over time in organizations and all over the world. So when we start, right, so the x-axis is the time and the y-axis is the size of the data. So when we start, we have a certain amount of data. So you can think about 2014 or something like that. And as we start our data science process, and in the world in general, as time passes, we start to collect more and more data points about our users, about our transactions, etc. And eventually, in the world we live today of GPT-3 and other monsters, the data size explodes. And many papers show that in the future years, this phenomenon of growing data is only going to continue. Okay. But what if we can use only a fraction of our whole data sets, of our full training data, and still get the same performance? I guess this is my beard doing that, so I'll try my best. So imagine we can use only a part of this data, only a fraction of the data, and keep our performance. And this is the promise of the paper we are going to talk about today. So for the agenda, we're going to talk about walking through the paper. The paper is called Dataset Cartography. It's out of LNAI and Hebrew University of Jerusalem. We're going to explain the paper, go over the technicalities, and get an intuitive feel about what it does. And in the second part, we're going to talk about our journey with applying this paper on real-world applications. So this paper presents a new concept called training dynamics. Training dynamics are a set of metrics that we assign for each sample in our training data. And this is driving me crazy. So yeah. So a set of 3 metrics that we assign to every sample in our training data. And how do we do that? So the first thing we need is a deep learning model for classification. This method is specifically for deep learning models, classification models. The second thing we need is, while we are training the model, after every epoch, we freeze the weights of our model, we predict for the entire training set, and we put aside, we collect the true label probability. So I'll walk you through that. So let's see an example. So imagine we are training our classification model. We got to the end of the first epoch, and this is the prediction for our first training sample after we froze the weights after the first epoch. Then we can see the label here as 1. So we take and collect the true label probability. So the true label now is 1. We take the 0.4 and we collect it. Then we go on to the next sample. Again, we look up the true label probability and we collect it. What will happen eventually at the end of this process, we will have all the true label probabilities for the entire training set. We repeat this process after every epoch in our training until we get this matrix, which has as many rows as training samples and as many columns as epochs. And each value in this matrix is the true label probability of a specific sample at a specific epoch. So what do we do with this matrix right now? Using this matrix, we can calculate the training dynamics that we assign for each training sample. So the first one is called confidence. So there's fancy mathematics, but it simply means the mean prediction. So we take a sample, like a single row for the metrics we've seen before, we average it, and that's the confidence. So if on average we are predicting close to 1 over the epochs, that means that the model has high confidence in its prediction. The second one is variability. Variability is, again, taking the same row, we are taking the standard deviation. So a high variability value means that across epochs, the model wasn't stable. It was dancing around probability of 0.1, 0.9, 0.5, etc. for the same sample. If the variability is low, that means that the model has got it right from or predicted the value equally throughout the epochs. The last training dynamic is called correctness. Correctness, you can think about it as a number between 0 and 1, which represents the sample accuracy across epochs. So we count the times that the probability of the true label was the highest one in the prediction, and we divide it by the total number of epochs. So if we get a value close to 1, that means that from the first epoch to the last epoch, we always had the true label as the max probability predicted by the model. If we get 0, it means exactly the opposite. Once we have those 3 training dynamics assigned for each training sample, we can plot what is called the data map. So let's understand what we are seeing here. So each point is a sample in our training set. The x-axis is the training dynamic called variability. The y-axis is the confidence, and the color is defined by the correctness. Now, there are 3 sections of interest. So on the top left side, we are seeing the easy to learn samples. These are samples that the model predicted with high confidence. So on average, the prediction of the true label was close to 1. And it predicted it with low variability, meaning it got it right from the first epochs to the last epochs. These are the most obvious samples. On the bottom left, we have the hard-to-learn samples. The hard-to-learn samples are again of low variability, meaning they were stable across epochs, but the model predicted them, on average, predicted them wrong, or very, very far from 1. And the most interesting section is the ambiguous section. The ambiguous sections are samples that had high variability, meaning the probability wasn't stable across the epochs, and we have a confidence of around 0.5. So this visualization actually is not taken from the paper. This is our reproduction of this paper on a different data set. And just like Hanan did, you can go to this notebook. This code is open source, and this is available through a pip installable package. Part of the packages I publish, and it's a simple TensorFlow callback that you can attach to your models and calculate your data maps at home. So what does that have to do with shrinking the data, right? This is what we came here to talk about. How can we distill our data set to a smaller set, yet maintain our performance? So what they have shown in the paper is that if you focus your model on the ambiguous samples, you can take only 33% of the original size of your training data and get an equal in-distribution performance. In-distribution meaning the test set that was cut off from your original data, and even better out-of-distribution performance, meaning better generalization ability. Now, intuitively, when we think about it, if you will take the analogy of a student, if you focus him on the more ambiguous, more hard questions, it makes sense that he will perform better at the task, and they obviously compare themselves to other dataset distillation techniques, and they show great results. Next, the question is, okay, 33% is nice, but can we go even smaller? So the next step, they are doing, they are keeping the ambiguous section, but they are starting to shrink it. So they try 30%, 25%, 20%, and in the data set that they've tested it on, around 17%. What happens is the model stops converging. It doesn't even get to a local minimum or anything that they can do with. So at this point, they're asking themselves, okay, so how can we help our model converge? And what they do is add into the mix easy to learn samples. So they take the 17% and they start replacing some of those samples in the 17% with samples that are easy to learn in order to help the model converge. And they show that, again, using only 17% of the data with around 20% of the 17% replacements of easy to learn samples, they again achieve the same in distribution performance and even better out of distribution performance. So at this point, I think you can understand why we at DSG found this interesting. This can have a lot of impact over many companies that deal with huge data and have a lot of expenses on hardware dealing with huge data, on professional time dealing with huge data. And we decided to take it for a ride. So this is where the paper ends. And now we're going to go over our experience of applying this method on real applications. So the first thing I want to say, it's not so straightforward to distill a data set. It's not like I can tell you, you can go back home right now, take your whole data, take 17 most ambiguous samples from your data map, replace 20% of those with easy to learn, and everything will work fine. And in fact, in some of our testing, even taking like 20% randomly of the entire data was enough to replicate the results. But on the optimistic side, it does work if you find the right values for your data. So you can distill your data set, but it's not like you can take off-the-shelf values and it will just work. And the two other points I want to talk about, which is the main part of our second part of this lecture, is our further research we built on top of this paper. So the first question we asked, how much of the data map is attributed to the model and how much is attributed to the data? And why is this question relevant? Because if you think about it, when we created the data map, we created it using a specific model and the data set. And if it's fully attributed to the model, then once we distill the data, we can't use that distilled data set with other models. But if we can fully attribute it to the data, then what we can do is we can distill the data set once, and we can continue our research freely using any models we'd like without any limitations. The second thing is how can we make better research decisions by inferring subproblems from the data map. So what do I mean by better research decisions? When we are iterating through models, there's the brute force approach of let's try different architecture, let's try different hyperparameters, let's try different features. But we don't have the luxury to do that because we need to deliver value to our clients fast. So we need to make smart iterations. We need to find what's wrong and treat that. So by using the data maps, we are able to find subproblems within our data set and create hypotheses about our next model iterations. So let's start with the second point, the model data attribution. So this is the data map that we've seen before. This is for the QNLI data set using the Distill-BERT model. And then we went and created another data map with a different model, in this case, the Distill-BERT model. And obviously, the points are the same points. They are the same samples, but they are obviously not located in the same place. So we asked ourselves, how much do these data maps have an agreement between them? I mean, how far are the points here from the points there? If it's attributed to the model or attributed to the data. The first thing we did, so we clustered the obvious clusters of easy to learn, ambiguous, and hard to learn, and we measured the adjusted mutual information, which is a number between 0 and 1. And the results weren't bad, but they weren't good. We saw like the score came out between 0.35, 0.38, 0.4 at best. But we didn't give up at this point because 0.4, it's not, we can't completely say that we can attribute it to the data. So we wanted to ask, where do these models agree and where do they not agree within this space of data maps? So we took these two data maps and combined them into a new one. what are we seeing in this data map? So the x-axis and the y-axis are the same, but now each cross in this data map is the average location of the point from the previous two visualizations. And the color basically says how much they agree on the location, because the color is a function of the distance of those two original dots to this average location, where dark points mean high agreement and bright points mean low agreement. And what we can see is, even though we had just a mutual information of like 0.4, and we know there is disagreement, we can see that most of the disagreement are not in the areas of interest, because when we distill our data sets, we distill them using the extremities, right? Using the most ambiguous and the most easy to learn. And we can see that these models do agree on the location of these extremities. But we didn't stop here. We said, okay, but distill Roberta and BERT are strong models. What happens if we add a third model, a really bad model, into the mix? So we took a third model, which is like basically slightly above a random chance in performance, and we've added it into the mix. So the plot, essentially the colors and everything is the same. We can see a lot more disagreement. So the new model attributed a lot of to this visualization. But again, we can see that the extremities, the most easy to learn and the most ambiguous, are still quite dark. At this point, we, instead of playing around, we start to take the empirical approach, and we distilled the data sets, the same data set we distilled with each model, and we trained the other models using the distilled data sets, and we did get good performance. So we did conclude that in the use cases that we have tested, we can attribute most of the extremities to the data and not to the model themselves. I must say that obviously distilling your own data, meaning the model, using the same model to distill and the same model to train later, had better results, but for practical applications where you are not trying to beat the 1% of the previous paper, it's good enough. Next, I want to talk about the data subproblems and how can we improve our research using the concept of data maps. So let's think a bit about what the data map means. What's the meaning of this space? So the data map gives us a little bit of insight about how the model learns the different samples. What's the learning journey that he went through the epochs? And when we take this space and we try clustering it using density-based clustering algorithms, then we can find that samples that the model sees as the same samples semantically or learning-wise the same will be clustered together. So you are free to cluster with anything you'd like, but for simplicity, let's focus now on the QNLI dataset and the two most obvious clusters, which are the hard to learn and the ambiguous section. Because essentially what we want our model to have is all easy to learn samples. So in the QNLI dataset, when we looked at distill Roberta, at distill BERT, and a third model which was very bad, and we examined the clusters of hard to learn and ambiguous, we've seen, so the QNLI dataset has question and sentence pairs, and we've seen that the sentences are significantly smaller on hard to learn samples. When we looked at the most ambiguous samples, we've seen that the sentences are very long. But this is not enough, right? There's like thousands of samples. The fact that you've identified something by merely looking at some samples is not enough. So this is like the identification phase. The next phase is quantification. Okay, you've observed a phenomena, but before you make an hypothesis around it, it's better to quantify it. So the next step, for example, would be to plot the distribution of the sentence length of hard to learn, plot the distribution of the sentence lengths of ambiguous samples, and plot them against the general distribution of all the sample lengths. And now you can make an hypothesis. If they are indeed separated, you can say, you know what, on my next model iteration, I'm going to focus on very short and very long or very long samples. And you can then see if your resolution or your hypothesis, after you implement it, if it had the effect that you wanted on the performance in the end. So again, this is like a very simple use case of sentence lengths, but you can imagine that in any data set you can find very interesting things in those clusters to help you make better research decisions and not iterate in the dark. So to summarize what we've talked about today. So the first thing we learned that you can distill your data set if you find the right values. You should take the time to do that. If it has any meaning to your organization to use smaller data sets, you should take the time and explore what are the right values for your data set and use that. It can have, for many organizations, it can have a great impact on spend and also on the environment when we think about all the crazy models that we train today. The second thing is we can distill data sets across models. So we don't have to stick to what we've seen in the paper that you distill and use the same model. It is possible to distill across models as well. And the last thing is that using the data maps and exploring the space that we get through those epochs, we can find subproblems in our data in order to make better research decisions moving forward. So I'll say at this point that obviously everyone can feel free to contact me, and thank you for listening.